Now, let us go to person, and we're going to create a hybrid model of a new type, ladies and gentlemen. I'm going to go to person, and I am going to add into person, ladies and gentlemen, a stock. And to do that, I'm going to go to the palette over here, and I'm going to drag in, ladies and gentlemen, a stock to that person. And that's going to be called weight, okay, weight in pounds, since we're in the States. Okay, weight in pounds, okay? And we're going to have a flow in called energy in. So Kurt, any luck there?
Sort of. It was visualizing it according to the location they had set, and then set their own location.
Oh, I see. Okay.
It set them all, it's like 45.0 and minus 96.0.
Okay, and that trace LN help you track that down?
Yeah.
It's your friend.
It is.
Yeah. Yeah. It's even though it's a geeky friend. Maybe because it's a geeky friend. Yeah. Okay. Okay, and then we're going to have flow out. Yeah. Flow out. Okay, oops, flow out. Or energy out, sorry. Energy out, excuse me. Okay. Energy out. There we go. So energy in, energy out. Okay, ladies and gentlemen. Okay, now I'd like to go put in place here a parameter. You notice the parameter is visible in the System Dynamics palette. In general, a given item might be in multiple palettes, and parameters are one of those things that transcend all three types of modeling. So you'll find them in several places. This parameter will be called energy expenditure coefficient. There we go. Okay, and ladies and gentlemen, the energy expenditure coefficient has a value of 0.01. It's a double with 0.01. Are we okay with that? Okay. Ladies and gentlemen, I would like to go to the stock. Now, stocks in System Dynamics represent accumulations. They represent the current state of the system. They often are where the inertia of the system is. Capture the current state and they take a while to budge. The way stocks are changed in System Dynamics and ODE modeling, compartmental modeling, is by the flows. It's the flows that are where the action's at, and they end up shaping the evolution of the stocks. A stock will go up as long as its flow in is greater than its flow out. Flows are in some quantity per unit time, quantity being the same thing as what's in the stock. So maybe the stock is kilograms or pounds, so energy in would be in pounds per unit time, and energy out similarly pounds per unit time. Okay, and this is representing accumulation of weight due to energy in and loss of weight. Ladies and gentlemen, so the initial stock value here should be 180 pounds. 180. Okay. Okay. Next, ladies and gentlemen, I would like to set what's called a first order delay, and what this is going to be is a decay from the stock, which is going to depend on two things. It's going to depend on the stock. So the output here, energy out, is going to depend on the stock. If one has very, very high weight for a given level of it's going to require more energy to maintain it than will if very, very lightweight. So we're going to have a link from weight to energy out, and then we're going to have a link from this energy expenditure coefficient that we added to energy out. So I'm going to put this up here on the board or on the screen. We're going to have energy expenditure coefficient, and we're going to link that up ladies and gentlemen, to energy out here. Okay? Boom, like that. Are we okay with that? People okay with that? Okay. Ladies and gentlemen, this is a construct known as a first-order delay. It's one of the key constructs of system dynamics. It's one of these building blocks we build models out of, and it represents a negative feedback. As weight goes down, the energy out will tend to go down, and therefore weight will go down more slowly. It won't go down as quickly. It pushes back against the original change. So energy out here, the formula for this is energy expenditure coefficient times weight in pounds. So energy out is energy expenditure coefficient times weight in pounds. Okay? That's a self-limiting flow. As weight goes down, for a given energy expenditure coefficient, the rate of energy expenditure will go down, so weight will go down less quickly. Okay? Remember, weight will go down, weight in pounds will go down if energy out is greater than energy in. They'll be drawing down the weight. By contrast, if energy in is greater than energy out, the weight will be rising. This is a self-limiting, this first order delay is self-limiting because as the energy rushes out, it will tend to lower weight in pounds, which will tend to lower the rate of energy expenditure. In other words, weight in pounds will be lower, therefore energy expenditure times it will be lower. Okay, so ladies and gentlemen, that's the formula for energy out. And next, I would like to create a variable. Mark my words. Now we're starting to do something very unusual. We have a variable here called energy from food, ladies and gentlemen. Okay? So this energy in contrast to energy out, it's just for energy in, we're going to have it be dependent on energy from food, and the energy from food is going to be hitched up like this. Okay? So we're going to have a variable, and it's go directly to energy in. Are we okay with that? So if energy in equals energy out, the stock will be unchanged. If energy out is greater than energy in, the stock will be declining. If energy in is greater than energy out, the stock will be rising. This is like the flow into your bathtub, this is like the flow out. If the flow in is faster than the flow out, and gallons per minute coming in is faster than gallons per minute going out, if the flow in is larger than the flow out, the bathtub will be rising. And so it is with this weight in pounds. If the flow out is faster than the flow in, if you've got water trickling in, but the water is coming out of the drain of the bathtub really quickly, the bathtub will be falling. If the rate of water out is the same as the rate of water going out is the same as the rate of water coming in, the stock will be in equilibrium. Does that make sense? Okay, so energy out, energy in. Okay, ladies and gentlemen, we're done a lot of the features of this basic weight, but we want to make it very visual, ladies and gentlemen, because we are visual creatures, and our stakeholders are often visual creatures. We like to be able to show things visually. It can help enhance the chance we'll build a useful model that actually gets used if it communicates in a compelling way. So ladies and gentlemen, I would like to go to this oval, and we were supposed to have named this, I was supposed to have named this body oval, okay, to indicate that it's a body, as compared to the head, which lies above it. Okay, ladies and gentlemen, okay, I would like now to go down. We had previously set this body oval to have a fixed radius. Do you remember that? Yeah. Okay, now the radius, ladies and gentlemen. Okay, I've got to watch out for my throat. Let me just move this up a little bit. Okay. Okay, so I have less risk of shouting. Okay, so we're going to leave the radius y what it is, but we're going to have people's girth depend on their weight. Is that okay? Okay, so ladies and gentlemen, for the radius x, I would like to give a formula. Now, what do I have to do? I'd like you to tell me. What do I have to do to put a formula here? Can I just start typing it? I have to change it to dynamic. Okay? And the formula is going to be, ladies and gentlemen, 3 times, and you can be careful about it, 3.0 times weight in pounds divided by 180.0. Okay? Okay. Okay. Are we okay with that? We okay? Okay. So as they gain weight, they will grow larger in an x direction, right? Are we okay with that? Well, okay. I'm not asking that normatively, but they're going to. It's an unfortunate feature, but weight has impact on girth. Yeah. Okay. Ladies and gentlemen, now I'd like to go to person. I'd like to go to person, person as a whole. So over here, I'd like to go to person. Oh, look at that. There's an error. Let's go check out what the error is. Okay. Energy from food is not used but expected. Oh, what's wrong here, folks? You tell me. What do you think's wrong? It's telling me energy from food is not used. What did I forget to do? I hitched it up, and actually it is connected, but the problem is I didn't specify a formula for energy in that uses it. And the formula for energy in should be energy from food. Okay?
A quick question for you. What's the difference between variables and parameters in this sense?
Okay, great question. So, question was, sorry, I just realized the audio quality is going to be poor. I've got to get out my audio recorder. The difference between variables and parameters is a substantive one, and it's a multidimensional one. So the first salient difference is that variables, so parameters have a very specific purpose in life. Parameter encodes an assumption about the model, and it communicates that assumption from the point of, so if something contains a parameter, let's say person contains a parameter, the parameter serves to communicate that assumption from where the person is created, like when a birth occurs for them, or when they're in that initial population, and we specify parameters in that population. Do you remember that? In the population, you specify the assumptions to have for each person. The parameter serves to encode that assumption and to communicate it from where the person's created to that person. So from when the place that they're born, we encode, we call add population, we give the parameters, or for that population, we specify the parameters there. And typically it's a static thing. We only very rarely, in my experience, modify parameters after they're specified. They're typically static things, much the same role that they play in statistics. You specify the parameters for a distribution, right? And they're not being updated over time. We may sample using MCMC, sample from values of parameters, but we're not changing the parameters of a statistical model within that statistical model. So parameters are typically static quantities. If they're updated, it's very rarely. the case and very rare in time, typically. And they encode an assumption and communicate that assumption. A variable, by contrast, is typically an aspect of a state, of a person or state of the system that is modified over time. Its job is to encode something that is modified over time. So do you remember when we had a variable yesterday and the day before, in fact? We used it quite a lot, and it was spelled in an American fashion. What was it? Color, indeed. Color was being updated on an ongoing basis. Do you remember that? Color was being changed. Whenever you change state, you change color. It was an aspect of your state. And so it is with variables. And this energy from food is going to be modified as people eat food, as they go to a convenience store, go to a grocery store. That's going to be modifying their energy from food. And so it's an aspect of their state that's updating over time. It just happens not to be amenable to easy description with either a stock or a state chart. Now, let me distinguish between those two. A stock, ladies and gentlemen, is typically used to denote a continuous quantity, a quantity that's varying continuously. And I'll try not to get on a bully pulpit too much with you, but I will say that that traditionally system science has been pursued by differing and sometimes warring camps. So the people who practice system dynamics tend to be a different community than the people who practice agent-based modeling traditionally, than the people who practice discrete event modeling. And you'd be surprised, but traditionally they rarely go to each other's conferences. They are rarely aware of what each other is doing, and they're each kind of going off on their own methods. This is talked over the past few decades. And unfortunately, what this has tended to mean is that a given student only gets trained in one method. An outcome of that is that people generally only know one method and only apply one method. And with a tool like AnyLogic, we actually mix the methods together. And although you won't read about it in too many books, it's extremely effective. So stocks here describe continuous quantities that vary continuously over time. That's not redundant. Continuous quantities. So things like weight, it's expressed as a double precision value, right? My weight varies. Or maybe it'll be another quantity we often treat as continuous, which is my viral load. Or maybe it's my CD4 count. Or maybe it's my level of risk that I perceive in the environment around me from bird flu or something like that. So it's some continuous quantity, and it varies continuously over time. Now, AnyLogic in general, by default, has things varying over time. But it's this ability to represent continuous quantities, particularly in a regulatory context, in a context where there's kind of processes shaping this weight over time that are regulatory in nature. As the weight changes, it changes the energy out, for example, which regulates the weight. We know that's very characteristic of a lot of metabolic and indeed immune system processes. We get exposed to pathogen, it stimulates activation of T cells and stimulates this cascade of proliferation, which leads to T cells multiplying and fighting the immune, as part of the cell-mediated immunity, fighting the invading pathogen. There's all these regulatory processes in the body, and we can represent them often with exquisite clarity using stocks and flows, because the quantities fundamentally are underlying quantities are continuous, and they have regulatory processes associated with them that can be described, say, with differential equations or stocks and flows, equivalent mathematically. And yet, in the same model, we might use state charts to represent quantities that are categorical in nature. In the sense that a state chart, right, you have these categories, and you transition between the categories over time, again, in continuous time by default. And state charts are very nice for representing the fact that, susceptible, infected, recovered. You're not dealing with an underlying reality that you're trying to model. You're not trying to characterize the situation in a way that's continuous. Rather, it's a set of categories. And that's also an extremely useful capacity, and it can be captured very nicely with a state chart. Meanwhile, we might use a variable like energy from food for capturing a quantity that's only updated not continuously but discontinuously. Like every meal, I have a certain energy that I take in from food that applies for the next little bit. But or will you have my color? My color is set at discontinuous boundaries when it changed state. It's not varying in a continuous fashion that would be amenable to depiction with system dynamic stocks and flows. Rather, it's being updated on an occasional basis. And it could be a continuous quantity, or it could be a discrete quantity. It might be a count, or the number of times I've been infected thus far in a recurrent type of illness. Pertussis, for example, the number of times I've been infected with pertussis. Or it might remember something about the number of times I presented for care. So we'd use a variable for that rather than stock. It's not a continuous quantity, it's a count. Or because it's only being updated discontinuously. It's not being updated in a continuous way over time like stocks are. So variables are different from parameters in the sense they're being updated. They're an element of state and being updated over time. They're not so much encoding assumptions to start with, but rather aspects of state. And they live together and sort of complement what you can represent with a state chart, categorically, and with a stock and flow in terms of continuous processes over time. Is that helpful? Okay, great. And again, it raises great prospects that now we can, for the first time really, readily intermix these things. And you'll tend not to find many models that do that with, in a really fulsome way. But this will be one of them, the one that stands before us, the one, ladies and gentlemen, that before the day is out, you will have built to fruition. Okay? Okay, ladies and gentlemen, may we go now to, we'll shrink down person. Okay. Let's go to person, and I would like in person to go to an area that was highlighted previously by Nick. And it has to do with movement. This person will move with an initial speed of 1 meter per second. They will be on foot. Okay? And they will be striding. Okay? Are we okay with that? Okay, ladies and gentlemen. Okay, so here we have it. Why don't we try to run this model? This is a good, when you have a model, ladies and gentlemen, run early, run often. It's by running it that you see things, you learn what causes what. Before you add some more mechanism, try running it like this. And then you can, with greater clarity, see what that new mechanism has changed when you add it. But more than that, you can also find bugs quicker. If you've added a whole whack of stuff and there's some weird problem, you don't know where to start. What did I change? I changed this, that, the other thing. I changed these things over here and those things there. If you're adding it just a bit at a time and running it, there's fewer things you've changed. So if something goes wrong, you have a better clue about where to start looking. Okay? So it also lends itself to a more sort of interactive experiment where you can evolve your ideas about what's needed. Sometimes you learn, oh, I'm doing something silly early on. Let's go dive down to a person here. You'll notice now if we go to root main, we'll see all these things here. What are these things? What things lie before us? These are actually the different agents. Some of those are supermarkets, some convenience stores. Let's go down to population. And you'll see here people's weight changing over time. We can actually graph. This is a person who's wow, they're losing weight in a serious way. Why is that? Because they're not eating right now. Okay? Okay. And before we have lunch, we will have them eat. Okay? I think. Don't worry, I won't make you lose weight like that. Okay, this one poor person is down to 90 pounds. Okay, before cachexia sets in, let's stop that. Okay, so let's now bend ourselves towards towards food seeking. Okay, so I'm going to stop.